Luke Houghton.
And Lara Houghton.
And we're going to be talking about the process control of Mario. What really happens? So, everyone knows about the Mario game. I'm sure many of our generation played it when we were young. And what you do is you get Mario and you jump around and explore different worlds. And we'd initially thought about doing a PID controller that would control Mario so that he could get through the world with ease, each world by the computer. And we thought it would be great, but then we realized the problem. Whenever he goes down the sewers, he would go down the pipe, and then there's this room, and there's a bunch of coins, and that's completely ridiculous. So instead, what we wanted to do was something a lot more realistic, and that is we're going to talk about sewage.
Yeah, so here's a little diagram of a normal sewage process where you've got sewage coming in from industrial and domestic sites, and it comes in and goes through these processes that take out solids and begin to clean the sewage. And eventually it gets to this area. This is called an activation or aeration basin. In this basin, the aerobic bacteria that are grown in here digest the organic compounds in the liquid and clean the water. So if you were to drain the basin, this is what it looks like. You've got all these pipes. These pipes have little tiny holes, and air is pumped through these pipes to push little bubbles through the water so that there's a lot of oxygen to feed the bacteria so that they're able to digest the organic compounds. And this is what it would look like in operation. So here's another little close-up diagram of the aeration basin. As you can see, we have sewage with the solids removed coming in. We pump air through tiny holes and make a lot of bubbles, and they clean up the water so that we have happy fish.
So our objective that we want to accomplish for this project is to control the bacteria population so that we can have our clean water. Our manipulated variable is the oxygen concentration in the tank. Our actuator is going to be the 8 blowers, which we will activate as needed in order to control the oxygen flow. We assume that each one provides 1 milligram per liter of oxygen, and we'll be talking about the impact of that on the bacteria population. We also have a disturbance, which is the flow rate of sewage, and that will actually be pushing some bacteria out of the system. Here we have our transient bacteria balance, which balances the mass of bacteria in our tank. We got these equations from the article below, and we're going to just step through the important parts of it real quick. So first we have here XBH, which is the mass of bacteria, and we're going to be modeling how that changes with time. This first term here is the growth rate of bacteria in grams per hour. The most important term of the growth rate is going to be the concentration of oxygen in the wastewater, and that's what we'll be changing and using to manipulate the growth rate of the bacteria so we can have the correct set points. Then we also have the death rate of bacteria. This is just a constant amount of bacteria for this model, simplified model that just says how much bacteria will die in a given amount of time generally. And then finally we have the flow rate of bacteria out of the tank given by the flow rate disturbance.
So then we put our model into Python and we conducted a step test. And at first glance, we can tell it doesn't look like an FOPDT or SOPDT model. We can tell that because when we put in the same input at different times, we do not get the same output. You can see that when we put in 1.75 at the beginning and end, you have completely different bacteria concentration. So we attempted an FOPDT fit anyway, just to see what would happen, and we tried to optimize it, and it didn't work at all. You can see that down here, the model was not able to be fit with an FOPDT. So we implemented some disturbances with flow rate. You can see that there are 2 peaks, one in the morning and one in the evening, of the different amounts of sewage flow through the plant. And so we were able to implement those into our controller.
So one of the challenges with this changing flow rate is that the amount of oxygen needed to help the bacteria population stay alive changes. So what our controller does is detects the flow rate and then calculates the value of oxygen concentration needed to maintain a constant population, that's U bias. And then with feedback from the aeration basin, we can calculate with this PI type term, and we can multiply that term by our U bias, or our standard steady state oxygen concentration, to adjust the actual concentration of oxygen that's input by the blowers into the system.
And so we look at this little diagram and we can see where the transmitters will be placed and the controller. So we have a flow transmitter and a concentration transmitter sending a signal to the flow controller where we can change the oxygen concentration to control the bacteria population in the tank. So our results from our feed forward with PI type multiplier implemented worked pretty well. We can see our bacteria concentration didn't really have any overshoot. There's less than 1%, and it was able to fit to a set point pretty well. But we can compare this to a normal PI feedback control, and the concentration of bacteria is really hard to stay at a set point. It has a hard time doing that, and we got at most a 15% overshoot at one point at around hour 22. And so we saw that our feed-forward controller worked much better.
So in conclusion, the feed-forward control works a lot better than the traditional PID for this case because it's much better at rejecting the flow disturbance. However, our model is really interesting and we can control it really well with this controller, but we realized that in order to accurately model a real system, we would need to have a much more complex model, which would include things like ammonia concentration and measuring and modeling the concentration of organic compounds in the water. So a lot more work would need to be done to make a controller like this work in the real world.
Thank you very much.
Subscribe.